So just like aldehydes and ketones, esters can also do reversible condensation reactions. And this type of reaction is called a Claisen condensation. And the mechanism for this reaction is actually quite simple. So the classic version of the Claisen condensation that you'll see in many organic chemistry textbooks is where they take two molecules of ethyl acetate and treat that with sodium ethoxide, and then the last step will be protonation. I'll talk more about that in a second. So basically what's happening in this reaction is that you're actually deprotonating ethyl acetate. So you can see that you have three acidic protons over here. You're going to remove one of those protons with base, and I won't draw the curved arrows for that part of the mechanism, but we should know that we're going to get an enolate once we deprotonate that proton. And once we have the enolate, well, we know we could draw a resonance structure so that we would have a carbanion like this, so you could draw it either way, and we talked about that during our last class. And we said, well, you know, the carbon is actually the more nucleophilic of the two atoms versus when we're talking about oxygen and carbon. So we could say, okay, well, let's take this resonance structure and we'll draw our mechanism with that. So what's going to happen next is that this ethyl acetate that's been deprotonated to form an enolate, well, since it's done in sodium ethoxide, there's going to be an equilibrium. We talked about the equilibrium that exists because of the pKa of ethanol, the conjugate acid of ethoxide, and the pKa of ethyl acetate, which is somewhere in the ballpark. So both species will be present in equilibrium. So what's going to happen is we're going to have another molecule of ethyl acetate. Okay, and now that we have our carbanion, you can imagine, or excuse me, our enolate, you can imagine nucleophilic attack by this lone pair on the electrophilic center of another molecule of ethyl acetate. So what do we get at this point? Well, let me switch back to my black pen here. So at this point, we're going to draw out what we have, and we should have a tetrahedral intermediate. So at this point, we'll have a tetrahedral intermediate, and I'll draw out the whole thing. So we have our negative charge here. We have our methyl group, but now we've got we have an ethoxy group down here, which can serve as a good leaving group. So what's going to happen is we're going to regenerate our carbonyl, and we actually have a decent leaving group here. So we're going to lose ethoxide. And if I redraw this like this, what we have at this point is we have our product, well, what looks like our product, but we also have ethoxide present in solution because that was our leaving group. So what's actually going to happen is since we have two acidic protons down here, we're actually, since we talked about in the last class that a species like this, the protons are going to be very acidic, somewhere in the neighborhood of 10, whereas ethanol is going to have a pKa somewhere around 16. So since this is so much more acidic, we're actually going to deprotonate that, and we will reform a doubly stabilized enolate. So if I draw this back out, actually I should redraw these arrows. Let me see here. Let me redraw them like this. So our equilibrium is actually going to lie to the side of our product. We have very little bit of this. So let's draw our product out. So we have this, and we have deprotonated, so we'll have ethanol in solution. And this is step one in the process, and the second step is to add acid. And as you can imagine, all we do in that step is that we protonate this negative charge here to generate our final product. So once we treat that with H3O+, so this is the second step, then we end up getting our final product. So this is a Claisen condensation. And the product of a Claisen condensation is called a beta keto ester. A beta keto ester. And if you think about looking at the molecule like this, well, you have your alpha going from the ester, you have your alpha carbon, then you have your beta carbon. So beta, we have a ketone at the beta carbon, so beta keto ester, because esters take higher priority in nomenclature over ketones. So it's a beta keto ester. And actually, the driving force of this reaction, what pushes this reaction forward, because you see the reaction is in equilibrium the whole way until we get to this last step here. And this is a key step in the reaction. And the formation of this doubly stabilized enolate is what actually drives the reaction forward, because this is a very favorable process. So when you get here, it's important to point out that the arrow lies more to the left to give you this product versus this intermediate. So this is what drives the reaction. So over here, drives the reaction. And Klein talks about this in a little bit of detail. So this is a classic example of the Claisen condensation, where you take an ester and you treat it to condensation conditions, and you end up generating a beta keto ester. So I hope this helps when you're studying Claisen condensations.